So now started to introduce some theorems related to orderliness. And first is that previously we related the orderliness, defining the symmetry distribution in terms of quantile function. And indeed, if we rearrange it, we can another expression is that if the symmetric quantile average is always equal to the median, then for every epsilon, so then this distribution is symmetry. And because we're just defining the quantile average, so if we're replacing the symmetric quantile average with quantile average and replacing the median with gamma median defined here, and then we can define a new type of distribution called gamma symmetry distribution. And this distribution has a very nice property that it is always Lorentz gamma ordered. That means it is a distribution that it is not if gamma is equal to 1, then it is not symmetry, but it holds some symmetry structure based on due to the quantile average relation. And then the symmetry distribution becomes a special case of the gamma symmetry distribution when gamma equal to 1. And also for any right skew distribution, the quantile function satisfying this relation, and then this it can be used, and then it is also Lorentz gamma ordered. This can be used to prove some parametric distributions whose quantile function is very elegant, for example, the Pareto distribution. And furthermore, previously we say the monotonic decreasing distribution is always ordered, and then and here we can further prove that it is always second gamma ordered. And more importantly, this reveals a relation between orderliness and second gamma orderliness, because for a monotonic decreasing distribution, indeed it must be partial, at least partial bounded, maybe bounded, because this mode it cannot be extended, so it must be bounded. And if we consider the mode here, there is no mode within the interval. So basically, we can say that the mode number is closely related to the possibility of orderliness, because if we're redefining modality, then if the mode number is 0, it's 0, and then this distribution is always ordered and second gamma ordered. And if the mode number is 1, unimodal, and then the possibility of orderliness is very high, as we discussed previously. But if it is multimodal, although it is still possible that for example, if it is a symmetry multimodal distribution, then it is possible that it is ordered. But if it is a skewed, although it is still possible, but the likelihood is much smaller. And more importantly, previously in theorem 1, and we say that the order for a gamma order distribution, it must the probability of the first quantile, it must be greater or equal to the probability density of the second quantile. And for monotonic distribution, there is no such problem. But for a for a unimodal distribution, and then because the possibility of the first quantile, it must be greater than the second quantile, so naturally it forms a single mode. So in this way, we can say that although a gamma order distribution, maybe it is not strictly unimodal, but generally there should be a dominant mode within it, and other modes should be some small modes. And later, if we consider a gamma symmetry distribution, if we transform it with a convex function, and then the resulting distribution is always gamma ordered. And if the convex transform distribution, if the quantile function satisfying this, it can be even second gamma ordered. And theorem 7 also reveals a relation between convex transformation and orderliness. And since the phi is a non-decreasing convex transformation, and so if we for example, even if a distribution is non-ordered but relatively symmetry, I assume this is non-ordered, and then if we transform it with a convex function, as the second derivative of the convex function increases, for example, it will become more and more skewed, and eventually it will become ordered. So therefore, in a family of distribution, if we differ from symmetry, from relatively symmetry, and then to more skewed as such a two-parameter distribution, and normally it is the violation of orderliness typically only occur when the distribution is nearly symmetry. And Van Zewa's sense, and Van Zewa's introduce the convex transformation is in order to comparing the schooners of two distribution and defining robust measures of schooners and also kurtosis. And his approach is comparing the stochastic ordering between two distributions. And what we done here is during investigating the ordinators within a distribution. So it is conceptually similar. And more importantly, if we consider the violation of ordinators in 2018, Li Shao Wang Yang, for Chinese mathematician, they proved the Bayer's bond of any quantile for arbitrary continuous distribution. And this bond is also monotonic, and it is very, because I do not show here, it is monotonic, but you can draft by yourself. It is a little bit like this, yes, in this way, monotonic. And also Bernard, he further refined the bond for unimodal distribution, and this is also a monotonic function. And this monotonic bond has an important role. That, for example, this is the bond, and this is the actual quantile average function. So the actual quantile average function, it might not be monotonic, so the ordinaries might be violated. But however, because there is a bond, so the violation, this is impossible. This is impossible. And this might be possible, right? So this bond basically saying that although it is possible for the violation of ordinators, but the violation is bounded. And also even for higher Knuth gamma ordinators, these are all bounded by this bond. And because we have such a nice relation for the ordinators, and it is and gamma ordinators, and so many distributions is valid, and even it is not valid, the violation is bounded. And therefore, we can investigate it, the ordinators, the impact of ordinators on weighted average, on other weighted averages. And first, we want investigating the existing weighted averages. First is the trim mean, and we can defining. Just like the quantile average, we can defining the trim mean inequality as here. For example, this is the medium. This is, for example, we can say that this is the medium, and then the second is this is the 40%, like 40% trim mean, 30% trim mean, and 10% trim mean, and mean. This is mean, zero mean and zero mean. So as the breakdown point becomes smaller and smaller, it should if the this trim mean will be closer and closer to the mean, and if a distribution satisfying this relation, it is called following the gamma trim mean inequality. And we can show that for a distribution following the gamma trim mean inequality, it is always the quantile average is always less biased and closer to the mean comparing to the corresponding trim mean with the same breakdown point. And more importantly, from this theorem, we can even deduce that the Winsorized mean is always greater or equal to the corresponding trim mean. That means, for example, if this is 40% trim mean, and maybe this blue one might be also 40%, but Winsorized mean it is closer and less biased than the Winsorized mean. And this result is because previously the Binek, he proved the Bayer's bond, and it is the worst case scenario. And here we show that for a distribution following the trim mean inequality, the Winsorized mean is always better than the trim mean in terms of Bayer. So we basically saying the average scenario, because the trim mean inequality is not a very strict condition. As I proved in the SI test of this paper, that a distribution is ordered following the ordinators, and then it will follow the trim mean inequality. And so because the ordinators is so popular in probability distributions, and so this so that means this explains why this Winsorized mean, if you test many examples, in both cases it will better than the trim mean in terms of Bayer's, and this explains the result. And then we can deduce new weighted averages based on the ordinators. We just split it, rearranging this inequality, and then we can first from the gamma ordinators, and we can defining a Brock Winsorized mean. For example, if we are saying that this is the sample, and then this is the main part, this is the trim part. For the Winsorized mean, we just saying that for the Winsorized mean, it is computing the main proportion, and then replacing the trim part with the extreme values. Okay, replacing with the extreme values. And for the broad Winsorized mean, it is also replacing the trim part, but it will become replacing with less extreme values. It is like this. This is the broad Winsorized mean. So it is similar to the Winsorized mean. Okay, it is like this. And asymptotically, we can prove that the Winsorized mean is always less biased than the corresponding broad Winsorized mean. And conceptually, this is not very difficult to understand because the replacing is not that extreme. And then from the second gamma orderliness, and we can further define deducing this inequality. And this inequality it suggests that, for example, this is the first block, second block, and it suggests that the block 1 plus the block 2, block 3 is always greater or equal to the block 2. So it means that if we're replacing the block 3 with block 2 and replacing the block 1 with block 2, and then this result will always smaller than or equal to than the original sample for right school distribution. And this is a nice result we want, because what we want is that we want to defining an estimator that as the breakdown point become smaller and smaller, it will be closer and closer to the population mean, but also it should follow a monotonic relation, so it should be always smaller than the population mean. So this is why we want to seek a relation that it should be smaller than the population. It should be smaller than the population than the original original sample mean if we're replacing that, and here we can find that we can say that this stratified mean, for example, 1, 2, 3, 4, 5, 6, and if we replace the corresponding stratified mean is just 2 plus 5. Yes, over 2, because we're replacing the first this with 2 and this with 5, and this is, and if it is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it should be 8, 5, 2, 2. It is just 2, 5, 8. Yes, it's just like that. It's just like that. So the stratified mean is always it is deduced from the second orderliness, and always smaller than the sample mean. Asymptotically, it is always smaller than the population mean. And then from the Knuth gamma orderliness, and we can further deduce this alternating binomial coefficients. And from that, we can deduce a binomial mean. And this binomial mean is much more complex, but we can give some example. For example, for if 1 minus negative 1, if j is equal to 0, and then 0 is equal to 0, and then so the first is and then 0 is equal to 1. Okay, 1, and then this is Knuth 3 choose j is equal to 0, 3 choose j is equal to 0, so it is 1. So the first choice, the first coefficient is just 0. And that means if 1, 2, 3, 4, 5, 6, 7, 8, then the first weight, we are assigning weight in front of each block. So the first weight is 0. And then the second weight, we can express that. The second weight, because it is negative 1, and times the 3 choose 1. Okay, so it is 3, and then because it is negative 1 4, so it is 4. Okay, so it is 4, and then it is 1 minus 1, and then times 3 choose 2. 3 choose 2, so it is also 3, and then it is negative 2. Okay, negative 2. And then it is 1 minus negative 1 times, okay, 3 choose 3, it is 1. Okay, and then it is 2. Okay, so it is like that. The first weight is 0, and then the second weight is 4, the third weight is minus 2, the fourth weight is 2, and then by symmetry it is also 2 minus 2 plus 4 times 4 plus 0. Okay, so this is the computational method for the broad Winsorized mean if nu is equal to 3. and for other 4, 5, 6, 100, and it is basically like this, and this weight is an alternating, because due to the alternating binomial coefficient, yes, and negative and positive, alternating it is like that. And then so we do not repeat it here, and because this Bloch-Winsorized mean is this binomial mean is based on the Bloch approach. And if we use a single quantile, we can define a stratified quantile mean. It is very similar to the quantile mean, very similar to the stratified mean. It is just based on the Bloch quantile approach, because stratified mean is based on the Bloch approach. For example, maybe here this is it may be like this. Yes, it may be like this is a Bloch, but the quantile mean becomes a single quantile. We just consider. Yes, for example, if there are 2 single quantile, maybe they're like this. If there are 4 single quantile, maybe like this. Yes, maybe like this, 4 single quantile. So so this and also we can defining that deduce that the stratified quantile mean is always less biased compared to the this is indeed identical to the stratified mean, because it is the order is 2. So and so the stratified quantile approach is in terms of bias, it is better than the Bloch approach, but Bloch approach also has this advantage in terms of variance, but we do not discuss in this paper. And this is the bias of this estimator, of all these estimators we discuss as